And I believe I gave you one example already, but let's recognize the cases where we need to apply what we do here. The first case is when we have 0 to the 0, infinity to the 0, 1 to the infinity. Example. I believe I did number 58 last time. Let me do number 62 now. Number 62, limit x goes to infinity of e to the x plus x to the power of 1 over x. How do we compute this? This is equal to, we do it this way first. We let y equals to, we cannot attack that directly, e to the x plus x to the power of 1 over x. Then I apply natural log. That's 1 over x, natural log of e to the x plus 1 plus x. Then I will apply limit x goes to infinity of natural log of y equals to limit x goes to infinity of natural log of e to the x plus x over x. You will see when x goes to infinity, this will be infinity over infinity case. So I apply L'Hopital rule. On the top, when I do the derivative, I will get 1 over e to the x plus x times e to the x plus 1 over 1, which simplifies to be e to the x plus 1 over e to the x plus 1. Now this is still infinity over infinity. So I apply another L'Hopital rule. Oh, I'm sorry, over this is x here. Sorry. I apply another L'Hopital rule. I cannot simplify that anymore. So I apply another L'Hopital rule. I get e to the x over e to the x. Okay. While on the left-hand side, we have, this is natural log of limit of x to infinity of y. Oh, you're right, plus 1. That's plus 1. And you can do L'Hopital rule again if you like. This is infinity over infinity, right? You can do L'Hopital rule again. Even though that's not the only way though. Now, the thing is, once you are here, do not say this is equals to 1. No, it is not true. It is true, later on it will becomes 1, but you cannot say the next step is 1. Because if you write it this way, you are saying, if you write it this way, you are saying that e to infinity over e to infinity equals to 1. That's what you mean. Once you stop writing the limit notation, it means you replace the variable by the value. But that's not what you are saying here. That's not what you're trying to say here. What you are trying to say is that's already 1 even before you plug the x in. So the next step, you're supposed to show limit x goes to infinity of 1 first, which is equals to 1. That's how you're supposed to write it. Okay? But Thomas, you know, I can do it in my head. Trust me, me too. But I still have to, when I grade you, I have to grade you based on what you write, not based on what I think you want to write. Okay? The definition of bias is judging somebody based on other thing than written. Okay? I have to grade you based on what you write, not based on how much I know you, not based on how smart you are in doing things. Well, because if that's the case though, then can I just teach you that way too? I really wish it, you know. Okay, can I just teach you so fast? I do all the shortcuts, and then I just say, you know what I mean. No, you don't want me to teach you that way, right? So don't do that to me. Okay, you still need to show your work in correct order. Okay. Yeah, I know what you mean, but I still have to correct you if you write it incorrectly, because it is possible when you don't write it properly, you mean something else. Let's say, for example, this one, limit x approaching 2 of x squared minus 4 over x minus 2. You may say this is equals to 4. It is true, the answer will be 4. It is true, the answer will be 4. But how do you get that though? If this is all you write, you are saying that when you plug in 2 in, that's equals to 4. That's what you are saying. Because once you take off the limit notation, once you stop writing the limit notation, it means you already plug in you already substitute the variable by the value. That's what it means. Okay. Now I believe that's not what you meant, right? I believe that you did it in your head so fast that you factor x squared minus 4, and then you cancel x minus 2, and then you plug in 2 into x plus 2. That's how you get that 4. Okay. Unfortunately, in math, when it comes to proving, you need to show that. Okay. When it comes to computing, you need to show that. Say what you mean what you say. Okay. If you write it this way, it means you substitute the x by 2 and compute it, and you say the value is 4. But no, 0 over 0 is not 4. Okay, I say it once. I think this you will see this again at least twice in my lecture, either today or next week before the test. But trust me, later on after I give your test back, I will have some students coming back to me and complaining, Thomas, you take off points here. I say, yeah, but you take too many points there. Well, that's little points for me, okay, because what you say there is not correct. Okay, but I hope I don't get that from this cluster. I hope I don't get that from this cluster. Well, we are not done yet here, because what we need is limit x going to infinity of y. That's e to the 1, which is e. Okay, but what is y? y is e to the x plus x to the power of 1 over x. That's what the y is. And therefore, this is the limit. Okay, let me ask you to try. Let me ask you to try number. Let me ask you to try number 58. Actually, not 58. Number 66. Did I do that number 66? I don't remember. Maybe not yet. You try number 66. Limit x goes to infinity of 2x minus 3 over 2x plus 5 to the power of 2x plus 1. Okay, you do it. Let me give you 5 minutes from here. I don't think we can finish it in 5 minutes. Maybe not. But at least you get a big story already. So we come back at 7:37. Let y equals to 2x minus 3 over 2x plus 5 to the power of 2x plus 1. So ln y will be 2x plus 1 times natural log of 2x 3 over 2x plus 5. Apply the limit condition, x going to infinity of this natural log. I will modify that a little bit into indeterminate form. Okay. Now, by the way, it was indeterminate form earlier because this guy, when x goes to infinity, this guy goes to 1. And this guy goes to infinity. Now, 1 to the infinity is one of the indeterminate form. That's indeterminate powers, right? Okay. Now, here, when x goes to infinity, this goes to 0. This goes to 1. But natural log of 1 is 0. So you get 0 over 0 case here. You get 0 over 0 case here. So I will apply L'Hopital rule. Apply L'Hopital rule, then I will get limit x goes to infinity of, on the denominator, I'll get negative 2 over 2x plus 1 squared. While on the numerator, I will get the reciprocal of blah, the reciprocal of the argument, times the quotient rule, which is 2 times the denominator minus 2 times the numerator. Now simplify. Let me let it be on the denominator for now, only positives. X goes to infinity. Negative 2 over 2x plus 1 squared, and on the top, actually my 2x minus 5, one of them cancels, so I get 2x minus 3, x plus 5, right? while on the numerator I will get 4x plus 10 minus 4x plus 6. Okay. X going to infinity of, on the numerator here, I get 16 divided by 2, I get 8 on the top with 2x plus 1 squared, big over 2x minus 3, 2x plus 5. Then from here, you get infinity over infinity again, right? So you can do L'Hopital rule if you like, but I don't think that's what I will do. I don't think that's what I will do. What I will do instead, I will divide by x squared on the top and divide by x squared at the bottom. So I get 2 plus 1 over x squared over 2 minus 3 over x, 2 plus 5 over x, which will give us negative 8 times 2 squared over squared. It's negative 8. But on the left hand side, that's limit x goes to infinity of natural log of y. Okay, so natural log of limit of y will be negative 8. So limit x goes to infinity of that ugly thing. I don't even know what's that anymore. It's so ugly. What's that? Minus 3 plus 5 plus 1. So 2x minus 3 over 2x plus 5 to the power of 2x plus 1 equals to e to the negative 8. Okay, I would really like to show you another method to do this problem. But before I show you that other method, let's look back to number 58. I wonder if I did this problem before. 262. Did I do the problem? No, I didn't. Number 58. Limit of x going to infinity of 1 plus a over x to the power of dx. I didn't do this yet, but you can try. You should try. You should try to do this problem using limit law. Technique. Okay, you should try that using limit law technique. Now, I will show you how to do this problem, number 58, without using limit law. Okay, alternative method, we know, we memorize that limit x goes to infinity of 1 plus 1 over x to the x equals to e to the 1. Okay, now what I want to do is to modify this becomes 1 over x. Okay, and this into something x. That's what I will do. Okay, is known. So I start with limit x goes to infinity of 1 plus a over x to the power of ex. I will do this. If x goes to infinity, okay, uh, then then what happened is 1a over x can later on be seen as, this can be seen as 1 over x over a. Is it right? Remember, I try to get this pattern here. Okay? Okay? So I will write it this way. This is limit x goes to infinity of 1 plus 1 over x over a to the bx. Now I will write this x here also as x over a times a. Now then what I plan to do is I will call this my u later on. This will be my u. Okay, that will be my u. So let u equals to x over a. Okay, now since x goes to infinity, right, then x goes to infinity, then x over a will still go to infinity. Actually, I should say x over a goes to infinity for a positive. For a positive. You will see later on, even when a is negative, it still works. Okay, let's deal with the positive case first. Okay, so then I can write this way then. Limit x approaching x over a goes to infinity, 1 plus 1 over x over a to the x over a times ad. But the right hand side, the one here, let me do substitution. U goes to infinity, therefore is 1 plus 1 over u to the power of ad. This is the whole set there to the power of ad. Thomas, what happened if a is negative? Let me use blue color. For a being negative, oh, thank you. Oh, this should be 1 over u here. Like that. Now suppose the a is negative. So negative a is positive then. Is it right? And x approaching, keep on using it. X approaching infinity implies implies negative x over a also approach infinity. Cool. Now, what happened then? In this step here, limit x going to x over a, negative a, x over a going to infinity. This is 1 plus 1 over x over a, right? To the power of x over a times ab. What happens if a is negative? So using the same substitution for u, then this will be limit negative u goes to infinity, 1 plus 1 over u to the u a b. But if negative u goes to infinity, then 1 over u goes to what? Goes to 0 anyway. Right? That goes to 0 anyway. I use this color here. So 1 over u will go to 0. Okay, so then it will match with, eventually you will see this is e to the ab anyway. I don't like my argument. Something's missing there. Something is missing there. I don't like my argument. I will look for it. I will look for some missing. But I just can't really tell where's it missing. I don't like this argument here. Let me be honest with you. I don't like my argument here. I don't like my argument here. Yes, 1 over u will go to 0. It is true if that's the case. But the same thing with 2 over u, the same thing with 3 over u. But if I have 3 here, the number will be, the result will be different. So I cannot really argue that way. I cannot really argue that way. Okay. Now suggested homework from here will be from 6.8b will be from number 55 to 67. What else? Number 7374. number 87. Number 87, use my technique. Two methods, the limit natural log and my method. Okay, let me take a little break. I don't know, I feel really super not feeling that well today. Let me take a little break. Right now is 7:56. I will be back at 8:05. Or maybe a bit more. Okay, let me start again. The argument that I give you here, it's float. So the argument I have only applies when A is positive. When A is negative, there's a way to do this when A is negative, but apparently what I did here needs further explanation. Justification, I should say. Yeah, but I believe when you do that limit log method, you will get this answer. You will get that answer. Okay. What are the two methods? The first method is the limit log, the one I taught you so far. The first method is use the limit of log of y. So you let y equals to that expression, this thing here, the way you did this, And the second method is you modify to get limit u goes to infinity of 1 plus 1 over u to the power of u. Knowing that those are the two methods. So if we memorize, we can use that in the test. Yes. Yes. If I happen to ask you a question in which that you can modify the question into this, then go for it. Okay, then go for it. I'm sorry. I think before I move on to chapter 7.1, I would like to also show you the equivalent statement of what we had earlier. Limit x going to infinity of 1 plus 1 over x to the power of x. We know this is equals to e. But there's another one that is equivalent to that. Limit x going to 0, 1 plus x to the power of 1 over x. This is also equals to e. In fact, let me spend some time. To prove this. Let y equals to 1 plus x to the power of 1 over x. Natural log of y equals to 1 over x natural log of 1 plus x. It's like this. If you take the reciprocal here, if you substitute this to be u, then this will be 1 over u. But 1 over u will go to 0. Okay, so what we have up here and what we have down here are actually the same statement. this statement here and this statement here is very, very close to each other. Okay, if I replace the 1 over x becomes u, so this becomes u, right? This becomes 1 over u, this becomes 1 over, this becomes 1 over x, which is our u, that becomes 0. To be more precise, that's 0 positive. Okay, now what I want to show you there is that these two things, these two formulas on the top and the bottom here are actually equivalent. So limit natural log of y equals to limit x going to 0, by the way. X going to 0 of natural log of 1 plus x over x. And then I apply L'Hopital rule. This is 1 over 1 plus x over 1 on the left hand side. That's limit, natural log of limit. And this is equals to 1. Right? Therefore, limit x going to 0 of 1 plus x to the power of 1 over x equals to e to the 1 or simply e. Now, this is actually what we use to prove the negative case, positive or negative case of what we have up there. I think that's how I will do it. I think that's how. I think that's how I will do it. Okay, but still, it still needs some justification there. Now, in number 87, I mentioned earlier that in number 87, we have maybe I should say this thing. I should say, basically, we try to prove that limit n goes to infinity of 1 plus r over n to the power of nt. This is equals to e to the rt. That's what we need to show now. So you will see then proving this thing here can be done using two methods. The limit natural log using the first method, or you can modify it here and there the way I did up here. Okay, now the nice thing, of course, down here, the r is the interest rate, which will be positive. Okay, so the issue of what happens if the numerator is negative, there's no problem there. Okay, that's for 6.8. Let me just stop there. I will go on to 7.1. 7.1. This is integration by parts. Integration by parts. In my class, I will shorten that to IDP. Idea. Let u be a function of x and phi be a function of x also. Now, according to product rule of the derivative, u phi, the derivative of u phi is equal to u prime phi plus u phi prime. In other words, the derivative of u phi respect to x is equal to du dx times phi plus u d phi dx. Okay, now that's the derivative form. The differential form, this is derivative. The differential form, you multiply it by dx. The differential of du phi, the differential of u phi is phi du plus u d phi. Now, if I integrate the left-hand side, actually each side, if I integrate each side, the left-hand side becomes just u phi. Now that gives you the idea of integration by parts, in which integral of u d phi, integral of u d phi equals to u phi minus integral of phi du. That's our integration by part. Now, the ability of the integration by parts opens a very big doors to a lot of other integration possibly done. Okay, now for the next maybe 20 minutes, I will do problems from the book using our textbook method, the standard method of teaching this integration by parts. And then after that, I will show you something called tabular method, which our textbook doesn't teach, but it is being taught in other textbooks like Thomas Kaplu's. Yeah, it is taught in Thomas Kaplu's. Okay, let's do a problem like number 4. Number 4, integral of y e to the 0.2 y dy. Now we need to decide which is our u, which is our d phi. Usually we choose our u to be the one when we differentiate eventually goes down to 0. So in this case, I will choose this to be my u, and this will be my d phi. Okay, u equals to y. My d phi equals to e to the 0.2 y dy. Now, what I need is to find, so once I have my u and my d phi, I need to find my phi and du. I need to find my phi and du. Okay, let's put that in practice. So if u is y, then du equals to dy. Can you explain why you decided y to be u? I choose my u to be the function that the derivative will go down to 0. Okay, if you keep on doing the derivative, it goes down to 0. But it's actually more than that though. I have to say that by some practice, then you will see who should be the u, who should be the d phi. It does take some practice. But what I can tell you is that for now, we will choose the u to be the function or the expression that when you keep on doing the derivative, this goes to 0. While this guy here, if you do derivative, you will always have the e. You will always have the e. You will always have the e. It can never get killed. Okay. Now that's for now. That's for now. Later on, we will have more case in which it could be not the case. Like what happened if both of them, one of them is sine x and the other one is e to the x. However you choose your u, however you choose your v, neither one of them whose derivative will eventually go to 0. Anyway, coming back here, so dv is this guy, so the integral of that, the antiderivative of that will be 1 over 0 0.2 e to the 0 0.2 y, which is equals to 5e 0 0.2 y. Now then, according to the formula of my integration by parts, okay, this is equals to u v minus integral of v du. Take a look. This is my u v minus integral of v du. I think this should be y. Now then from there is just going further. This is 5y e to the 0 0.2 y minus 5 times 5 e to the 0 0.2 y plus constant. Let me factor the 5 and e to the 0 0.2 y. That will be y minus 5 plus constant. Number 8, integral t squared sine beta t dt. You will see a polynomial. If you have a polynomial with exponent, then polynomial will be your u. Because exponential function, however you do the derivative, will not go down to 0. Now, likewise, in this number 8, you have polynomial and trigonometry. Right? If that's the case, then polynomial will be the u, the trigonometry will be the dv. The antiderivative of f, if integral of fx dx is fx plus t plus c, then integral of f ax, if you have the coefficient, that will be 1 over the coefficient. Okay, we did this last time. And I think we also did this in your turn-in homework, right? So let's see what happened here. I will do like my u equals to t squared, my dv equals to sine beta t dt. So du will be 2t dt. My v will be 1 over beta times negative cosine dt, theta t. And this is equal to u v, so t squared times -1 over beta cosine theta t, there's my uv, minus integral of phi du. Let me simplify a little bit. This is negative t squared over beta cosine beta t plus 2 over beta integral t cosine beta t dt. Now, the thing is, you will see that this is not integrable directly, but it's doable by integration by parts again. So I will do the integration by parts again there. Okay, but I cannot use uv anymore though, because I already used uv. Let me use u1 and phi1, okay, just to distinguish that. So u1 equals to t, d phi1 will be cosine beta t dt. So du1 will be dt, v1 will be 1 over beta sine beta t. So I will continue. This guy is negative t squared over beta cosine beta t plus 2 over beta parenthesis u1 v1 t over beta sine beta t minus integral of v1 du1 1 over beta sine beta t dt. This is negative t squared over beta cosine beta t plus 2t over beta squared sine beta t. I think that will be minus, let me just do integration at the same time. That will be plus 2 over beta cubed cosine beta t plus constant. Okay. That's integrated. And actually, most of these are basically those kind of questions. Yeah, so it does take a lot of practice. Okay, it does take a lot of practice to do this. And maybe I write it as a note. And this note is super important, note. Integration by parts enables us to integrate functions, integrate functions in the past, which we only know its derivative. Let's say, for example, one of the classic example is this one, integral of tangent inverse x dx. Now we don't know what is the integral of tangent inverse x. There's no formula. Okay, there's no formula for that. But we know the derivative of tangent inverse x. The derivative of tangent inverse x respect to x is 1 over 1 plus x squared. Now that's what we will use. This is my u, and this is my dv. Okay, so u equals to tangent inverse x, dv equals to dx, such that the derivative of u, which we know, right, is 1 over 1 plus x squared dx, the phi will be x. Now, take a look. Then using integration by parts, I will get x tangent inverse x, that's the u phi, minus integral phi du. Now, if you notice, the guy on the right-hand side, the second term here, is actually doable by substitution. Okay, it's doable by substitution. This will be x tangent inverse x minus 1/2 natural log of 1 plus x squared plus constant. Okay, now in our textbook number 10, you actually see that similar question. Number 10, we have integral of sine inverse x dx. Now let me ask you to do this problem. Okay, let me ask you to do this problem, and then once you're done with that, I would like you to try number 20. After number 10, I would like you to try number 20. Number 20 is integral of x tangent square x dx. Okay, that should take you 5 minutes, another 5 minutes, 10 minutes. So I'll be back at 8:50, but you work on that first, please. Can you start? This one here, my u equals to sine inverse x, my dv is dx, so my du equals to 1 over square root of 1 minus x squared dx, my phi is x. So my integral then becomes x sine inverse x minus integral of x over square root of 1 minus x squared dx. Let me do a substitution. U equals to 1 minus x squared, so dw is negative 2x dx. So 1/2 dw is negative x dx. So this is x sine inverse x. That will be plus integral. And you pull the 1/2 out. dw. Oh, you know what? That's w to the power of negative 1/2 dw. It's x sine inverse x plus w to the power of 1/2 plus constant. Substitute the w. That's square root of 1 minus x squared plus constant. Number 20. What about the 1/2? 1/2 coefficient multiplied by 2, right? Yeah, you get 1/2 times 1/1/2. See right? I mean the integral of this from this exponent here. Will give you this guy stays here, but later on they cancel. Okay, see if I skip little step, you get confused, right? So don't skip your step, because I may get confused. No, just make it reasonable. At times I understand when you skip little steps, but don't skip too many steps at once. Okay, now, coming back here, number 20, I get my u equals to x, my dv equals to tangent squared x dx. So my du equals to dv, I'm sorry, dx, and my phi equals to, this one is not easy, huh? This is not easy. To integrate, there's no integral for tangent squared x though. So I will see this as secant squared x minus 1 dx, such that the phi will be the integral of that will be tangent x minus x. Am I right? The derivative of tangent is secant squared, right? Okay, then I get this is equal to integral of 1. Is it okay? Integral of 1. Oh, how did I get secant squared x minus 1? Okay, 1 plus tangent squared x equals to secant squared x. That's the identity. The second identity of Pythagorean identity. So u times phi, I use x. X times u times phi minus integral of phi du. That's x tangent x minus x squared. What is the integral of tangent? Anybody remember what is the integral of tangent? That's this is negative natural log of absolute secant x plus 1/2 x squared plus constant. Let me do it aside here. What is the integral of tangent x? Integral of tangent x dx equals to integral of sine x over cosine x dx. If my u equals to cosine x, then my du is negative sine x dx. So this is negative integral du over u, which is negative natural log of absolute u plus constant. But my u is cosine x, right? I will bring this negative exponent to the front, so this will be cosine x to the power of -1, the reciprocal of cosine x. But the reciprocal of cosine x is secant x. That's how we get that. Okay. Anyway, I continue here. I will simplify. I get x tangent x minus 1/2 x squared minus natural log of secant, absolute of secant x. Don't forget plus constant. Now, with the remaining time, I would like to teach you what somebody else called tabular method, integration by parts by tabular method. It's not a new type of integration by part. No, it's not a new type of integration by part. It's just the way we structure them. It's just the way we structure them. Okay, it's just the way we structure them. Now, I will do a problem using long way, and then I will simplify to show you what happened when we write it in a table. Let's say, for example, I want to do integration by parts for integral of x cubed times sine 2x dx. Yeah, I will do this, but in between, I will not do simplification. Okay, I will show you the long way, the previous way of doing that, without simplifying them, and so that we can see the structures, and that will bring us to tabular method. Okay, if this is what you want to do in your test, of course, simplify. Now, I will start with, let my u1 be x cubed, my d phi1 be sine 2x dx. du1 equals to 3x squared. d1 is 1 negative 1/2 cosine 2x. Such that after this first integration by part, I will get x cubed times negative 1/2 cosine x minus integral of phi du, negative 1/2 cosine 2x times, I should have dx here, 3x squared dx. This part, the first term here, I will just leave it like that. I will not simplify. You can simplify it yourself later. Minus integral of 3x squared times negative 1/2 cosine 2x dx. So I basically switch the position of this guy and this guy. Is it okay? I basically switch that. Now, I will do the second integration by parts. u2 equals to 3x squared. d phi 2 will be negative 1/2 cosine 2x dx. So du2 will be 6x dx. phi2 will be negative 1/4 sine 2x. Okay, such that now we get x cubed times, I get x cubed times negative 1/2 cosine 2x minus bracket u v minus integral of phi du. Let me reorganize them right away. 6x times negative 1/4 sine 2x dx. This will be x cubed negative 1/2 cosine 2x minus 3x squared negative 1/4 sine 2x plus integral of 6x negative 1/4 sine 2x dx. I will do integration by part the third time. So u3 equals to 6x phi 3 d phi 3 will be negative 1/4 sine 2x dx. du3 will be 6 dx. phi3 equals to positive 1/8 cosine 2x. So this becomes, let me shift this a bit to the left so that I have enough space on the right hand side. Plus 6x times 1/8 cosine 2x minus integral of 6 times 1/8 cosine 2x dx. I hope you are following me. Okay, I will play stupid now. I will do integration by parts again the last time. So u4 equals to 6. d phi 4 equals to 1/8 cosine 2x dx. The derivative of u4 is 0, while phi 4 equals to the integral of this is negative 1/16. No, actually positive. Positive 1/16 sine 2x. So if I copy everything all over, minus u v minus integral of 0 dx, which is 0. okay, which is 0. Now imagine if you notice that this is my very original u. This is my u1. This is my u1. That's my u1. Right? Do you see that? X cubed is my u1. While this guy here is v1. This is my u2. This is my v2. u3, v3, u4, v4. As if I can actually put it this way. If I redo my integration, I rewrite my integration. Integral is integral of x cubed sine 2x dx. This is my u, right? You keep on doing the derivative. You keep on doing the derivative. 3x squared, 6x, 6, until you get 0. This is my dv1. When I integrate that, I get 1 negative 1/2. When I integrate that, I get negative 1/2 cosine 2x. Integrate that again, 1/4 sine 2x. Integrate that again, 1/8 cosine x. Integrate that again, 1/16 sine 2x. And I stop because it's already parallel to 0. Then notice that the sign is actually alternating. Plus, minus, right? Okay, so you will see that the first product is actually this product here in the positive sense. The second product is the negative of this. The second product is the negative of this. The third product is the positive of this. I think I should say the third term is the positive of this product. The fourth term is the negative of this product. Okay, so you can see that the integration by parts, basically you choose one term or one factor as the one you keep on doing the derivative, and the other one you keep on integrating. Okay, now when do we stop? We stop when the derivative goes to 0. Okay, now let me repeat. Suppose I do this using tabular method. Suppose I do it with tabular method. This is what I get. And the answer is that. Of course, don't forget plus constant. So let's look back to number 4, for example. Number 4, tabular method. Integral of y e to the 0.2 y dy. The first one I do derivative. The second one I do integral. until it is parallel to the 0. So this is equals to 1 over 0.2 e to the 0.2 y minus. Remember, the product should have alternating signs. Minus 1 over 0.2 squared, which is 5 squared, e to the 0.2 y plus constant. This is equals to 5 e to the 0.2 y minus 0.5. Oh, I missed the y on the first one. I missed the y from here. 5 e to the 0.2 y plus constant. And you can factor the y e to the 0.2 y out. You get 1 minus 5 is constant. Okay, this is what I meant by integration by parts by tabular method. It's not a new integration by parts, no. It's just the way we structure it. Okay, so instead of writing u, dphi, keep on doing that. Okay, we focus on integrating and differentiating. Number 8. Number 8. We did number 8 already, but I will do it again, this time using tabular method. Derivative 2t to 0, so I stop here. Okay, the integral of sine is negative 1 over beta cosine beta t, integrated again. Integrated again. So the solution is negative t squared over beta cosine beta t. This one here. Okay, now then the second one, take the opposite of this product. The opposite of that product will be plus 2t over beta squared sine beta t. And then I'll take the positive product here. It will be plus 2 over beta cube cosine beta t plus constant. Let's compare with the answer we have above. Where's that? Here. But you see, when you did this one, it's a bit painful, right? That's a bit painful. It takes you a lot longer time compared to my tabular method. So I'm not saying that method is wrong, but if you are at one day you want to go to differential equation, then you better be fast with your integration by parts. You do a lot of integration by parts in differential equations. For the test, are you going to ask to do the long method? No, doesn't matter. You can use long method, you can use the short method, either one. But don't complain about time. Don't complain about time. If you choose to use long method, you know that you will be slower. Okay? So tabular method is there to help you doing it faster. Now, let me see if there's other type of question we can do. Thomas, can you do all integration by parts using this method? Yes, but the modification in some cases may not be something you want to deal with right away. Yeah, it's too early. You need to do some practice first. And then on Monday, when we come back, we do this, we do more problem from here. Integral, number 24, integral from 0 to 1, x squared plus 1, e to the negative x dx. Okay, We have polynomial and exponent. Polynomial is the one I do derivative. Exponent negative e to the negative x, e to the negative x, negative e to the negative x. So this is equal to negative x squared plus 1 e to the negative x minus 2x e to the negative x minus 2e to the negative x from 0 to 1. Right? This is the positive product, the negative product, positive product. Okay. When x equals to 1, you know what? Before I do that, let me factor the e to the negative e to the negative x out first. Okay, so I will get x squared plus 1 plus 2x plus 2 from 0 to 1. When it is 1, I get negative e to the negative 1 times 1, 2, 3, 4, 5. No, 1, 2, 4, 5, 6. So this will be 6 minus negative when x equals to 0. When x equals to 0, that will be just 3. That will be 3 minus 6 over e. Or you can just write 3 minus 6e to the negative 1. That's what's the file. This way, instead of having our energy or effort being consumed by integration by parts, we can look at the big picture that we are computing the definite integral. Thomas, what if I try to do the same problem on the tangent inverse in your example? Integral tangent inverse x dx. You still can do this. The problem is when you do the derivative for the tangent inverse, though, it will never go down to 0. Okay, I'm not saying that it's the weakness of integration by parts by tabular method. It's that you need to know how to modify the word. Notice that if I look back, the integral of this, take a look here. The integral of that is equal to the product of these minus the integral of this. Let me repeat. The integral of the original integral here, this integral here, is equal to this guy without integral minus the integral here. Let's look back. Integration of parts. This example here, right? This integral is equal to the product of this minus the integral of this. Okay, so what if that's the case, Thomas? In other words, then at times, we may not be able to get down to 0. So for example, on the left-hand side here, I do the derivative. I will get 1 over 1 plus x squared. The integral here is x, right? Okay. This means what? This is x tangent inverse x, right? The product of this minus the integral of this. Minus the integral of x over 1 plus x squared dx. Do you see the structure? If you go diagonally down, no integral sign. If you go horizontal way, you have integral sign. Right? And then, well, we did this problem before. You can just continue, right? You don't need integration by parts anymore here, right? You just do substitution. If you take a look on sine inverse, integral of sine inverse x dx, the same thing actually happens. This will be 1 over square root of 1 minus x squared. This is x. So this is equals to x sine inverse x minus integral x over square root of 1 minus x squared dx. And then from there, you go on. Okay. Now, why do I want to teach you this? Because at times you need to be aware if in case the product of this, the product of horizontal one is something you can integrate, then you better stop the integration by parts and do it as a regular integration. For example, for example, question number 12. I will show you more questions later on. And for me, to be honest with you, if you get it, it is fun. If you don't get it and you look at me, it's frustrating. So you need to exercise, okay? You may need to look at your notes during this weekend. Okay, number 12, integral of p to the 5th natural log of p dp. I decide this is my derivative 5p to the 4th. This integral, this is 1 over p. Oh, I'm sorry. Integral of ln is not 1 over, no, this is the derivative. No, this is not correct. This is not correct. I need to modify that. This is integral of natural log of p times p to the 5th dp. The derivative of ln is 1 over p. Right? Okay, now the integral of p to the 5th is 1/6 p to the 6th. Now, then you realize if I go horizontally here, it becomes simple 1/6 p to the 5th. If I go horizontally. So instead of keep on doing that, what I will do is, I will say this is 1 over 6p to the 6th natural log of p minus integral 1 over p times 1/6 p to the 6th dp. This is 1 over 6p to the 6th natural log of p minus 1/6 integral of p to the 5th dp. 36p to the 6th plus constant. What if we do tabular method diagonal way until integral side reaches 0? Never. Never. We can never integrate up to 0. Even if you have 0, when you integrate it, it becomes constant. Right? Don't you think so? Integral of 0 is constant, right? Okay, but there's no way for you to integrate up to 0, never. Never. Okay? So we are done with the solution here. Now I will show you an example where it will never go down to 0, and there's no way for us to simplify. Integral, for example, e to the x cosine x dx. To make it more interesting, let me make it 2x here and 3x here. What do you think? Now the thing is, neither one of them, when you differentiate, will go down to 0. And the integral of e will always have e. The integral of trigonometry sine cosine will be sine and cosine thingy. Under no way they will simplify the way we had this thing earlier. Under no way it will simplify nicely here. Okay, so what happened? Let's see. Let's see. Suppose I do the derivative for, because neither one of them actually goes down to 0, then it actually doesn't matter which of the factor you will use the derivative on. Okay, I choose to do derivative on e to the 2x. This will be 2e to the 2x, 4e to the 2x, while this one here is 1/3 sine 3x. This is negative 1/9 cosine 3x. I will stop there. Why? Here's the thing. Okay, this guy is now equal to, my computer must be so tired. I don't know what's wrong. I don't know what's wrong. This is equals to this product. Okay, that's equals to 1/3 e to the 2x sine 3x minus the product here. Negative 2/9 e to the 2x cosine 3x. Now the plus, right? But I go horizontally, so I have integral plus integral of 4e to the 2x times negative 1/9 cosine 3x dx. Let me make it nicer. So what I actually have on the left-hand side is e to the 2x cosine 3x dx. On the right-hand side, I have 1/3 e to the 2x sine 3x plus 2/9 e to the 2x cosine x minus 4/9 integral e to the 2x cosine dx. Now, why do I stop on the third line here, Thomas? Because on the third line here, you actually have the integral, your original integration, except that now you have extra coefficients. Do you realize that? See, this guy times this guy is what you have up here. Okay, so what, Thomas? Well, so we have the following situation. Give me a second. Sometimes I don't want to color too much because it may be confusing later on. Now suppose I call this my I. Suppose I call this, you see this integral here is the same with this one, is it right? Okay, so I can say now, if suppose I call this I, this will be I plus 4 over 9I equals to 1/3 e to the 2x sine 3x plus 2 over 9 e to the 2x cosine 3x plus a constant. Now, can you follow me so far? Basically, my original integration is equals to something plus a coefficient of the same original equation. So I fold it to the other side. But then on the left-hand side, we get 13 over 9I equals to that thing. So the I, which is our original integration, the integral e to the 2x cosine 3x dx is equal to 9 over 13 of the whole package on the left-hand side, on the right-hand side. So that integral now is done. Equals to 3 over 13 e to the 2x sine 3x plus 2 over 13 e to the 2x cosine 3x plus another constant, let me call that C1. Not C anymore, not C anymore. Let's say, for example, I do number 36. What I show you here, this last question, last example, not exactly this example, is very important as your foundation in differential equation class math 275. So if you are planning to take differential equation math 275, then you better be good with integration by parts and fast. In general, you need to be good with your integral. Okay, but what slows down a lot of students in differential equation is when it comes to integration by parts, because you spend so much time with that u dv v du thing. You know, once you know how to do it with tabular method, it becomes a lot faster, and you can focus on the technique instead of being confused when do I start Thomas. Number 36. In differential equation later on, in differential equation, where will this be very crucial? One of the difficult part called Laplace transform. When you use Laplace, when you do Laplace transform, it's basically the type of integration, not exactly the same, maybe even more complicated. Number 36, integral of e to the s sine t minus s ds from 0 to t. So t in this case is a constant. S is the variable. To help me not to confuse it, let me change the s becomes x so that I don't get confused, or you don't get confused, to be more precise. So I will integrate this as a definite integral first, okay, and then later on I plug in the 0 to t. Consider integral e to the x sine of t minus x dx. The integral, oops, the integral here is e to the x, e to the x. I'm sorry, the derivative. The integral will be cosine t minus x. The integral here will be negative sine t minus x. So this is equal to e to the x cosine t minus x, this product here, minus negative e to the x sine t minus x and then plus this integral, plus the integral of negative e to the x sine t minus x dx. Oh, I have to keep on moving to the left, to the right. Let me move it here. So this is now, this integral now is equal to, if this is my I, this integral now is e to the t cosine t minus x plus e to the, not e to the t, e to the x, e to the x, e to the x sine t minus x minus integral of e to the x sine t minus x dx. But that guy, the last term is I. This is I. Right? So then I move it to the left hand side, it becomes 2I equals to that, plus constant. So I now equals to 1/2 e to the x cosine t minus x plus 1/2 e to the x. I divide both terms by 2. Sine t minus x plus another constant. But I'm not done yet. I'm not done yet because the original question is integral from 0 to t of e to the x sine t minus x dx. Right? I insert the limit of integration now. So on the right hand side, it will be, actually I can factor 1/2 e to the x here, right? Cosine t minus x plus sine t minus x. Plus t. So this is equal to 1/2 e to the x cosine t minus x plus sine t minus x from 0 to t. When x equals to t, when x equals to t, this will be 1 plus 0 here, minus when x equals to 0. So that's 1/2 e to the t minus 1/2 cosine t plus, I'm sorry, minus 1/2 sine t. Okay. Now, integration by part is one very important integration in technique of integration in calculus 2 and in math especially. So I don't want to go too fast here. Okay, if you look at the book, if you look at the book, I can actually cover this section and done if I don't teach you tabular method at all. If I don't teach you tabular method at all, I'm done right now. Okay, I'm done. But you will never see the structure, which is more important. Okay, we use this a lot later. Now, so your suggested homework from here. Your suggested homework from here. Call that 7.1a will be from number 3 to number 35. From number 3 to number 35. If you think you can do using tabular method, go for it. If you try using tabular method and doesn't work, then you use long method. And then feel free to ask me, let's say during this Saturday, on this Saturday from 8 to 10, I have my office hour. Okay, send me an email though so that I can tell you the link to come to Zoom. Or you can send me an email also, Thomas, how to do tabular method using this question, for this question. And I will show you the tabular method in. Okay, if you have any specific question from this homework, suggested homework here, that you want to do, you want me to show the work, let me know. But on Monday next week, I will continue from number 37 style. But everything after here is just a variation, a further variation of integration by parts. Okay, that's it today. See you then on Monday.